Spatial data can give us a great deal of information that may not have been immediately obvious. Using surface analysis with elevation data, for example, it's possible to derive information and identify features that were not readily apparent in the original surface. These could be contours, the angle of slope, the steepest downhill direction, the aspect, the shaded relief, the hillshade, and the visible areas using the viewshed to find out if you can really see for miles and miles. All of that information from just height values. These continuous data sets can play an important role in spatial analysis. This could be in finding suitable locations or for cost paths or hazard mapping, such as avalanche estimation. You can also measure the flow of water across the Earth's surface, including deriving runoff characteristics, to understand drainage systems and derive watersheds. All of this information is vital to hydrological modelling, such as estimating the effects of change on ecosystems or for flood alleviation. Traditionally, data collected in the field, usually environmental measurements, consists of point measurements or sample collections at discrete locations. More recently, many automated monitoring networks have been set up, collecting many more data across more sites, across areas, at regular intervals, such as weather monitoring stations. So these data contain many more samples, but ultimately they're still samples of data, both spatially and temporally. It's unlikely that data is going to be collected at all locations continuously. That's going to be a tall order because there's always a finer resolution, either spatially or temporally. So spatial interpolation methods are used to estimate values at unsampled point locations using measurements from point locations in an area. Values are then estimated for a continuous surface, with the estimates being based in part on the known values that you have. Interpolation effectively fills in that missing information using the known information that you're getting from your sample points. It's needed when you have samples from something that's a continuous data set, or you're changing the resolution of your data. The cell size from a discrete surface requires changing. Interpolation is used in many areas such as climate modelling and environmental science, such as air pollution modelling, geology, or the mining of natural resources. There are two main groups of interpolation techniques: deterministic and geostatistical. Deterministic interpolation techniques create surfaces from measured points based on either the extent of similarity or the degree of smoothing. Geostatistical interpolation techniques, that are also called kriging, are a little more sophisticated and use the statistical properties of the measured points rather than modelling with a simple, smooth mathematical function. Fortunately though, in a GIS, all of that complexity is taken care of in the algorithm, so we can all use these approaches. Geostatistical methods can additionally give measured uncertainty at locations. The measurement of uncertainty is critical to making informed decisions, providing information on the possible outcomes of the values in that surface. Geostatistical interpolation relies on the spatial dependence of the phenomena being interpolated, assuming that two locations with similar distance and direction from each other will also have similar values. This relationship is known as stationarity. Although the term stationarity might be new to you, the concept of a relationship between location and value should be familiar. Spatial autocorrelation. So geostatistics is the statistics of spatially correlated data and uses semi-variogram modelling. Spatial analysis uses simple and complex statistical formula to derive mathematical models and help explain and model relationships between spatial phenomena. Using surfaces, you can identify features within data that help you explore and further problem solve within your data. Predictions are made from known data, but the accuracy of your results will be affected both by that input data, the quality of the input data, the choices that you make of the methods, and the assumptions that are required by those statistical methods. The ability to predict data using known samples is really valuable, but knowing how well you've predicted is perhaps even more valuable. That's what gives your results real meaning.